So far we discussed node and edge level features for prediction in graphs. Now we are going to discuss graph level features and graph kernels that are going to allow us to make predictions for entire graphs. So the goal is that we want features that characterize the structure of an entire graph. So for example, if we have a graph like I have here, we can think about just in words how would we describe the structure of this graph, that it seems it has kind of two loosely connected parts, that there are quite a few edges between the nodes in each part, and that there is only one edge between these two different parts. So the question is, how do we create a feature descriptor that will allow us to characterize the structure like I just explained. And the way we are going to do this is we are going to use kernel methods. And kernel methods are widely used for traditional machine learning in graph level prediction. And the idea is to design a kernel rather than a feature vector. So let me tell you what is a kernel and give you a brief introduction. So a kernel between graphs G and G prime returns a real value and measures a similarity between these two graphs, or in general measures similarity between different data points. A kernel matrix is then a matrix where simply measures similarity between all pairs of data points or all pairs of graphs. And for a kernel to be a varied kernel, this kernel matrix has to be positive semi-definite, which means it has to have positive eigenvalues. For example, and as a consequence, it has to be a symmetric matrix. And then what is also an important property of kernels is that there exists a feature representation phi such that the kernel between two graphs is simply a feature representation of the first graph dot product with the feature representation of the second graph, right? So phi of g is a vector and phi of g is another vector, and the value of the kernel is simply a dot product of this vector representation of the two graphs. And what is sometimes nice in kernels is that this feature representation phi doesn't even need to be explicitly created for us to be able to compute the value of the kernel. And once the kernel is defined, then off-the-shelf machine learning models such as kernel support vector machines can be used to make predictions. So in this part of the lecture, we are going to discuss different graph kernels, which will allow us to measure similarity between two graphs. In particular, we are going to discuss the Graphlet kernel as well as the Weisfeiler-Lehman kernel. There are also other kernels that are proposed in the literature, but this is beyond the scope of the lecture. For example, random walk kernel, shortest path kernel, and many others. And generally, these kernels provide a very competitive performance in graph level tasks. So what's the key idea behind kernels? The key idea and the goal of kernels is to define a feature vector phi of a given graph G. And the idea is that we are going to think of this feature vector phi as a bag of words type representation of a graph. So what is bag of words? When we have text documents, one way how we can represent a text document is to simply represent it as a bag of words, where basically we would say for every word we keep a count of how often that word appears in the document. So we can think of, let's say, words sorted alphabetically, and then, at position I of this bag of words representation, we will have the frequency, the number of occurrences of word I in the document. So in the same way, a naive extension of this idea to graphs would be to regard nodes as words. However, the problem is that since graphs can have very different structure but the same number of nodes, we would get the same feature vector or the same representation for two very different graphs, right? So if we regard nodes as words, then this graph has 4 nodes, this graph has 4 nodes, so their representation would be the same. So we need a different candidate for the word in this kind of bag of word representation. To be, for example, a bit more expressive, we could have what we could call a degree kernel, where we could say, how are we going to represent a graph? We are going to represent it as a bag of node degrees, right? So we say, we have one node of degree 1, we have three nodes of degree 2, and we have 0 nodes of degree 3. In the same way, for example, here we could be asking how many nodes of different degrees do we have here. We have 0 nodes of degree 1, we have 2 nodes of degree 2, and 2 nodes of degree 3. So, and this means that now we would obtain different feature representations for these different graphs, and that would allow us to distinguish these different graphs. And now both the Graphlet kernel as well as the Weisfeiler-Lehman kernel use this idea of bag of something representation of a graph where the star, this something, is more sophisticated than node degree. So let's first talk about the Graphlet kernel. The idea is that, right, we want to represent the graph as a count of the number of different graphlets in the graph. Here I want to make a important point. The definition of graphlet for a Graphlet kernel is a bit different than the definition of a graphlet in the node level features. And there are two important differences: that graphlets in the node level features do not need to be connected, and also that they are not rooted. So graphlets in the Graphlet kernel are not rooted and don't have to be connected. And to give you an example, let me show you the next slide. So for example, if we have a list of graphlets that we are interested in, little g1 up to the little gn sub k, let's say these are graphlets of size k, then let's say for k equals 3 there are 4 different graphlets, right? There are 4 different graphs on 3 nodes, undirected, fully connected, 2 edges, 1 edge, and no edges. So this is the definition of graphlet in the graph kernel. And for example, for k equals 4, there are 11 different graphlets, fully connected graph all the way to the graph on 4 nodes without any connections. And now, given a graph, we can simply represent it as count of the number of structures, different graphlets that appear in the graph. So for example, given a graph and the graphlet list, we define the graphlet count vector f simply as the number of instances of a given graphlet that appears in our graph of interest. For example, if this G is our graph of interest, then in this graph there resides one triangle, there resides 3 different paths of length 2, there reside 6 different edges with an isolated node, and there exist no triplet of nodes that are not connected in this graph. So the graphlet feature vector in this case would be here, would have value 1, 3, 6, and 0. Now, given two graphs, we can define the graphlet kernel simply as the dot product between the graphlet count vector of the first graph times the graphlet count vector of the second graph. This is a good idea, but actually there is a slight problem. The problem is that graphs G1 and G2 may have different sizes, so the row counts will be very different of graphlets in different graphs. So a common solution people apply is to normalize this feature vector representation for the graph. So this means that the graphlet vector representation for a given graph is simply the count of individual graphlets divided by the total number of graphlets that appear in the graph. So if this essentially normalizes for the size and the density of the underlying graph, and then the graphlet kernel is defined as the dot product between these feature vector representations of graphs H that capture the frequency or the proportion of a given graphlet in a graph. There is an important limitation of the graphlet graph kernel, and the limitation is that counting graphlets is very expensive. Counting a k-size graphlets in a graph with n nodes by enumeration takes time order n raised to the power k. So this means that counting graphlets of size k is polynomial in the number of nodes in the graph, but it is exponential in the graphlet size. And this is unavoidable in the worst case, since subgraph isomorphism, judging whether a subgraph is isomorphic to another graph, is NP hard. There are faster algorithms. If graph's node degree is bounded by D, then there exists a faster algorithm to count the graphlets of size K. However, the issue still remains that counting these discrete structures in a graph is very time consuming, very expensive, so we can only count graphlets up to a handful of nodes, and then the exponential complexity takes over and we cannot count graphlets that are larger than that. So the question is, how do we design a more efficient graph kernel? And Weisfeiler-Lehman graph kernel achieves this goal. The goal here is to design an efficient graph feature descriptor phi of G, where the idea is that we want to use a neighborhood structure to iteratively enrich node vocabulary. And we generalize a version of node degrees, since node degrees are one hop neighborhood information to multi-hop neighborhood information. And the algorithm that achieves this is called the Weisfeiler-Lehman graph isomorphism test, or also known as color refinement. So let me explain this next. So the idea is that we are given a graph G with a set of nodes V, and we are going to assign an initial color C, superscript 0, so this is an initial color, to each node. And then we are going to iteratively aggregate or hash colors from the neighbors to invent new colors. So the way to think of this, the new color for a given node V will be a hashed value of its own color from the previous time step, and concatenation of colors coming from the neighbors U of the node V of interest, where hash is basically a hash function that maps different inputs into different colors. And after k steps of this color refinement, C capital V of capital K of V summarizes the structure of the graph at the level of a k-hop neighborhood. So let me give you an example and explain. So for example, here I have two graphs that have very similar structure but are just slightly different. The difference is this edge, and here the diagonal edge, the triangle closing edge, is different. So first we are going to assign initial colors to nodes. So every node gets the same color, every node gets a color of 1. Now we are going to aggregate neighboring colors. For example, this particular node aggregates colors 1, 1, 1 and adds it to itself, while this particular node up here aggregates colors from its neighbors 1 and 1 and it is here. And the same process happens in this second graph as well. Now that we have collected the colors, we go and hash them, right? So we apply a hash function that takes node's own color plus the colors from neighbors and produces new colors. And let's say here the hash function for the first combination returns 1, then 2, then 3, 4 and 5. So now we color the graphs based on these new refined colors, right? So this is the coloring of the first graph and this is the coloring of the second graph based on the hash values of the aggregated colors from the first step. Now we take these two graphs and again apply the same color aggregation scheme, right? So for example, this node with color 4 aggregates colors from its neighbors, so aggregates 3, 4 and 5, so we have 3, 4 and 5 here. While for example this node here of color 2 aggregates from its neighbor that is colored 5, so it gets 2, 5. And again for this graph the same process happens. Now again we take these aggregated colors and we hash them, and let's say our hash function assigns different new colors to these colors that are combined aggregated from the previous time step. So now we can take this original aggregated colored graph and relabel the colors based on the hash value. So 4, 3, 4, 5, 4, 345 is hashes into color 10, so we replace a color 10 here. And we could keep iterating this, and we would come up with more and more refinement of the colors of the graph. So now that we have run this color refinement for a fixed number of steps, let's say k iterations, the Weisfeiler-Lehman kernel counts the number of nodes with a given color. So in our case, we run this 3 times, so we have 13 different colors. And now the feature description for a given graph is simply the number of nodes of a given color, right? In the first iteration, all the nodes were colored, all 6 nodes were colored the same way. So there is 6 instances of color 1. Then after we aggregated the colors and refined them, you know, there were 2 nodes of color 2, 1 node of color 3, 2 nodes of color 4, and so on. So here is now the feature description in terms of color counts for different colors for the first graph and different colors for the second graph. So now that we have the feature descriptions, the Weisfeiler-Lehman graph kernel would simply take the dot product between these 2 feature descriptors and return a value. So for example, in our case, the Weisfeiler-Lehman kernel similarity between the 2 graphs is the dot product between their feature descriptors here. These are the 2 feature descriptors, and we compute the dot product, we would get a value of 49. So WL kernel is very popular and very strong, gives strong performance, and it is also computationally efficient because the time complexity of this color refinement at each step is linear in the size of the graph. It is linear in the number of edges because all that every node has to do is collect the colors from its neighboring nodes and produce and apply a simple hash function to come up with a new color. When computing the kernel value, many colors appeared in 2 graphs need to be tracked. So the number of colors will be at most the number of nodes in the network. So this again won't be too large. And counting the colors again takes linear time because it's just a sweep over the nodes. So the total complexity of computing the Weisfeiler-Lehman graph kernel between a pair of graphs is simply linear in the number of edges in the 2 graphs. So this means this is extremely fast and actually works really well in practice. So to summarize the graph level features that we have discussed, first we talked about the notion of graph kernels, where basically graph is represented as a bag of graphlets or a bag of colors. When we represent the graph as a bag of graphlets, this is very expensive representation because counting the graphlets takes time exponential in the size of the graphlet. At the same time, Weisfeiler-Lehman kernel is based on this k-step color refinement algorithm that enriches and produces new node colors that are aggregated from the colors of the immediate neighbors of the node. And as multiple rounds of this color refinement are run, the node kind of gathers color information from farther away parts of the network. So here we represent the graph as a bag of colors. This is computationally efficient. The time is linear in the size of the graph. And it is also closely related to graph neural networks that we are going to study later in this course. So Weisfeiler-Lehman is a really good way to measure similarity between graphs, and in many cases it is very hard to beat. So this concludes the today lecture, where we talked about 3 different approaches to traditional graph level machine learning. We talked about handcrafted features for node level prediction in terms of node degree, centrality, clustering coefficient, and graphlets. We talked about link level or edge level features, distance based as well as local and global neighborhood overlap. And then last, we talked about how do we characterize the structure of the entire graph. We talked about graph kernels, and in particular about Graphlet kernel and the WL, meaning Weisfeiler-Lehman graph kernel. So this concludes our discussion of traditional machine learning approaches to graphs and how do we create feature vectors from nodes, links, and graphs in a scalable and interesting way. Thank you very much.